A little pop-up comes up. Yeah, there he goes. Does it ask me? No, not yet.
No, it hasn't. No, it didn't ask, did it? It's still going straight in. Okay, all right.
Yeah.
Thanks everyone for attending this session. I'm Shakes, and we're in the Summer of AI doing the Day of Diffusion. And what we're looking at there on screen is a remarkably realistic image of 4 billionaires put together. You can look at my search to see what billionaires they are. It works well on Google. We tried Bing, it didn't quite work, but you can see there's some other interesting images that this model can produce. In terms of the mathematics and the implications of this model, I think the ability to do generative modeling has never been so powerful. And in a sense, what we can also look at is this idea of manifold learning as well with images. It's so realistic, and its ability to condition the data whatever way you like. So in this case, we take a model built out of images, and we can condition it on the fact that we want these 4 billionaires into a single image, and we get an incredibly realistic output. So the agenda for today is basically to go through maybe just an introduction to the model, what it does, where it came from, what it does, and what is it. Then we'll go into slightly more technical detail on how it works and why it works. We'll have someone else present the mathematical sort of basis of it, or the initial mathematical basis of it. And then the final talk will be on someone who's already started using it for medical imaging, which I'm really keen to see, as he's made some submissions to some very well-known medical imaging conferences already. So this idea, or this stable diffusion idea, has been extremely rapid. The paper is not even 12 months old, and the framework itself that's available fully open source and online is no more than 6 months, 6 months to 8 months old. So if you thought AI is already too rapid in development, well, it's just speeding up. And next week we'll try to cover Chat GPT, which is even faster now. It's faster in terms of take up. It took 5 days to get 1 million users for that model. And something like Instagram took 2.5 months. So some really incredible models that we'll cover in this Summer of AI. So without further ado, I'll pass it on to Professor Brian Lovell, who's UQ's head of computer vision, and he's gonna stop sharing. He's gonna take it from there. Thanks, Brian. All yours.
Okay, I'm just you've shown a good example of stable diffusion, and I've had a little play before. I'm just going to show you something a little bit different. So this is, hopefully you can see that. This is a girl on a beach towel on the beach wearing a hat. And apart from the fact that she's only got one arm, it's maybe not too bad. And it's interesting to see the towel in this case has a cutout. So what happened is I started out thinking things were working really well. So here's a girl in a hat on the beach, and that's what came up, which you'd have to say that's good. And I think you could probably say that it's how's just trying to get a I'll just stop that share and just restart that. I'm just opening it up so I can get a better view of it. So share that. Okay, so that should be okay. So if you can compare those images, this looks pretty good. One thing to note is look at the poor girl's hand. So if you look at it looks reasonable around the face, but there is some problem with synthesizing hands. In fact, great artists have problems with hands and so on as well, but that's something we'd be interested in repairing to do some surgery on her arm. So it looks good, but it does make mistakes. And as I said, okay, I didn't want a girl looking like this. I wanted her to be on the beach lying on a towel. and I kept pushing the system, and then you start to get these weird problems of generation. So it's good, but it sort of gets broken down if you go down a layer. But yeah, you really have to have a play with that, and I suspect that there'll be some playtime for this. But it's still absolutely amazing that you can basically describe a picture and it comes up with a very reasonable version of that picture. So we'll get out of that and we'll move into my slides. These were prepared late last night, so they're not particularly good, and I don't have a particularly good view of stable diffusion, so I'm really a novice as well, but I'll tell you what I understand at the moment. So let's see if I'll share this. Share screen, that will be this one, hopefully. I just get the right version. Okay, that should be right, I think. Okay, so stable diffusion. And so what this allows us to do is convert a text description into an image. And that's pretty amazing. So a number of people have commented that they didn't expect to see this happening for another 15 years. And that's sort of my view as well. I think the biggest thing from my point of view in deep learning over the last few years has been StyleGAN. And StyleGAN allows you to do like synthetic faces that are absolutely realistic. And I've been excited about that because of my work in face recognition. We've been doing a project on StyleGAN, and so has Shakes. And then along comes stable diffusion, and the most of that was released around the time of my birthday, which is in September, and the full codes come out in December. So this is really hot off the presses. It's very new, very exciting. And as some people have said, it probably shouldn't have happened for another 15 years, but it's already here. And in fact, it's already been sort of superseded because you can now do text to movie synthesis in the last month or so. So it's going forward at an incredible rate. And it's also already commercial on Jasper AI and Canva. So what I'm going to show here is I'm going to look at how we synthesize an image in general, and then look at StyleGAN for a little bit to see and talk about some of the stuff we're working on, and then we'll look at what happens with stable diffusion and what you can do with that. So I've got a new PhD student starting up next year looking at stable diffusion, and Shakes is looking into it. So it's hot off the presses and extremely exciting. So let's see about how can you synthesize an image. So let's take a look at a naive view. To synthesize an image, we generally start with random noise, and then we sort of modify it to some extent. So if you get a random noise, and imagine we have a small image, so say 256 by 256 color image, a random image would have a vector space of 256 by 256, which is the XY coordinates. Each pixel can have has 8 bits to describe its grayscale, which is 256, and then there's the 3 color planes. So there's 50 million possible values. So you could generate any 256 by 256 image you like by enumerating those 50 million possible values. But that's a very large space, and most of the synthetic images will not look like an image at all. They'll look like random noise. So this space is too large. What would be nicer is if we had a much smaller space where everything we synthesized with our random noise generator turned out producing a nice image. For example, it could be every random noise vector that we put in generates a face, or it generates a work of art. Okay, so obviously the works of arts and faces is a much smaller subset than the 50 million possible values. So as I said, this space is too large, and so this is our real space. And what we need to do is to find a subspace or a manifold within this space. So a manifold is a low-dimensional object that can be embedded within a high-dimensional space. For example, the surface of the Earth, where we all live, that's a manifold in the universe. So the universe is a very large place, and the surface of the Earth is a very small space within that, and only some of that represents human faces. Okay, so you can think of those as spaces, big spaces and small spaces. And if you're lucky, when you if you have a random number generator, you could force that random number generator to only get you places within the manifold. So imagine you've got a teleporter on Star Trek Enterprise, and you want to send somebody down to a planet. You don't want to have them landing 100 feet in the air and being killed as they fall. You don't want to synthesize them underneath the Earth's surface. You have to synthesize them on the manifold. And at least then, if their feet are touching the ground and they are synthesized in the right spot, then they've got some chance of surviving the trip. So we want a small space. But the problem is, until deep learning came along, we really couldn't figure out a good way to make those smaller spaces. Perhaps some of you can suggest a way to make this search space smaller. And a simple thing to do is to actually make the image smaller. So if we had a 10 by 10 pixel image or a 28 by 28 pixel image like in MNIST, we have a much smaller space. So the synthesis problem is less of an issue. But when we have high definition images, the space becomes enormous. So let's take a look at early versions of creating a small space for synthesis. So here we have the variational autoencoder for the MNIST data set. So in MNIST, we have handwritten digits, like we see sort of on the right there. And these images are 28 pixels by 28 pixels, 255 shades of gray. So instead of 50 million, we're looking at 200,000 possibilities for the bit pattern. And some of those bit patterns will be handwritten digits. So what we do with a variational autoencoder is we use a bottleneck. So we start with an input layer that equals the images, and then we move it along layer by subsampling and subsampling until we wind up with a bottleneck layer where there's only two weights. Okay, so basically the whole image is reduced to two values, X and Y, which is a two-dimensional subspace, whereas the original was it's 28 by 28 by 255. So you can see the dimensionality is about 200K, something like that. So we've made a very big space into a very small space. And this is compact space. And if we vary the values of X and Y in the compact space, the system will take those two values and convert them back from two dimensions back to the image dimensions. So we have basically a cone, which is like a UNet structure, which brings us down to a two-dimensional space, back up to a high-dimensional space. And now in this two-dimensional space, every time we pick a random number, we generate a handwritten digit. Okay, so this is like the manifold. So we're guaranteed to be producing a handwritten digit if we stay within this space. And everywhere we go, we get a handwritten digit. There's no holes in the space. And that's the beauty of the variational autoencoder. So obviously, this is a small space, doesn't represent artworks and so on, but this is, to me, the first sort of version of this sort of technology. Now, autoencoders had been around for a while, and then we had variational autoencoders. So what's the difference? So in an autoencoder, people could do this sort of encoding, but then the handwritten digits wound up in spaces, and there were lots of holes. Okay, so these spaces, they were not compact, and there'd be places here where if you did a random number, you would wind up in one of the holes, and it would not generate a sensible image. What was different with the variational autoencoder? It was trained to compact the space. So here's what you get with an autoencoder. With a variational autoencoder, it gets these regions here that correspond to digits from 0 to 9, and it shoves them all together as closely as possible, so there's no holes. Okay, so anywhere you go in that space, you'll get something reasonable. So that's an important thing. So you want a contiguous space. You don't want to have any spots in that space that represent rubbish. Through deep learning, we can do that with a variational autoencoder. So you put a random number in this latent space. And what does a latent space mean? It's a hidden space. So this is over here somewhere we have the image space, which we can see, and it converts it to another space that we don't really understand that represents the image. And here it represents the images in just 2 dimensions. And that's a latent space because it's within the network and we don't really have a good understanding what's going on there, but it basically is a compact space where all of the space is represents an image or an image of the style we want. So we want to extend the synthesis to high definition color images. And for a long time, synthesis was limited to quite small images. And then with, say, the progressive GAN and so on, people were able to synthesize much higher quality images. So ProGAN was a progenitor of StyleGAN and StyleGAN2, which were from NVIDIA, and they showed that you could generate totally synthetic humans, and that was a real landmark. And that's only December 2018. It seems strange talking about landmark studies that are only a year or so old, but that's how it is. And my student, Terry Chandran Wang, was working on this topic, and he's been working to produce a synthetic face databases for face recognition. You may know that face recognition using AI received a big blow in Australia because it was considered to be unethical to use people's faces unless you got their consent to use it for face recognition research. And traditionally with deep learning, people have grabbed faces off the internet and used those and scrape the faces. And now they're saying that for all those faces you've scraped, you'd have to actually find the person and then get them to write a document to say that they're acceptable. So for historical databases, that is impossible. And it's also pretty much impossible to gather new databases using that technique because your face database sizes have to be so large, like 300,000 identities. So getting consent from 300,000 people to use photographs of them for face recognition research is pretty much impossible. So in my case, I was sort of faced with the problem that we couldn't do anything in this area compared to my friends overseas because of the ethics concerns. But what I did do is get an ethics exemption for using synthetic faces. So if we can make a face using StyleGAN or StyleGAN2 and they're totally synthetic, it's effectively like a cartoon face, we can do what we like without consent for synthetic faces. So funny thing is, we did get into an ethics discussion on one of the papers we wrote. We made some faces and we were specifically making faces of ugly people. And some of these ugly people were of different ethnicities like Middle Eastern or Asian or whatever else. And there were complaints from the reviewers that it was unethical to talk about somebody from different ethnicity as being ugly, even though these were actually synthetic faces like cartoons, which was a bit surprising. So because the faces look so much like a real person, then if you say that person's ugly, then you can get into trouble by the PC thought police. So that's funny because that's the first time I've had an ethics application in AI, and then somebody accused us of being a little bit questionable in our ethics, even though everyone I was dealing with, every photo we had was not of a real person. Okay, so how do we, so we're doing some work here, and this is a paper we just published last week or something like that. And this is FaceCook, which is attribute controllable face generation based on linear scaling factors. So FaceCook is a play on the word Facebook. And so what we're doing here is we're cooking up faces, so synthesizing faces to order. So we can have a list of words and then generate a face that matches those attributes or words. Why do we want this? It's for building a face recognition database. So we want to have people who look Indian, for example, male, female, people wearing hats, people with smiling, people looking left, people looking right, and this sort of thing. So rather than taking a photograph of them, which is a lot of hard work, especially as we did this work during COVID, we could actually just generate the photographs from scratch using a StyleGAN method. So we're not using StyleGAN, or we're using the framework of StyleGAN, but we've modified it to greatly improve its ability to produce faces to order. So it's like going to a restaurant, you dial up faces a la carte and say, I want a face that looks like this, and it generates that face for you. And that way we can generate sufficient diversity within the database to be reasonable for face recognition training. And at the end of the day, we can produce a face recognition system that hasn't ever looked at a real human face. And that's the plan. We're well on the way with that. So what we want to do is we want to get samples and we want to control features such as pose and so on. So if we take a real human photograph, for example, we want to be able to put it into a another space. Now, if you think about image processing, if you're familiar with that, it's very common to do image upsampling and downsampling. And effectively, all that is putting things into a different space. So we change the number of pixels, and now we've actually changed the space and if we downsample, we make a more compact space. If we upsample, we make a larger space. The freedom of deep learning is we don't have to have something that's simply related by a quad tree or like a downsampling algorithm. We can use other sorts of algorithms to convert image space into a different space. So instead of the image space being just a downsampled image, it can be some other shape that has nice properties like disentanglement of say pose and expression and so on, and we find this sort of space, and that's what StyleGAN does. So we go into this latent space that can only generate faces, and if we take a random sample, we can generate a face, and then often if the space is well disentangled, we can add a vector to that space, and we can do a change, like it can rotate the face, change the expression, change the ethnicity, possibly change the gender. So it turns out that these things that are important to us semantically start to become disentangled in this latent space, and we train the system to produce these characteristics. So now we can modify the space, and we can do things like go from a young female to an old male, and we could put glasses on or take glasses off. So this has been known for a while, but the methods have been very flaky, and generally when you ask it to generate these sort of faces, you might only get 1 or 2% of the faces that come out being what you want. So you spend a lot of time doing synthesis, and most of the faces don't work, and the ones that do work are the ones you publish. So what we've been working on is to get a much higher hit rate. So 90% or so of the faces can be exactly what you specify. Okay, so if you look in this latent space, you'll find that the people's faces tend to form these sort of clusters that aren't fully disentangled, but and they have some intersections and so on. But basically, this is the space of people with glasses. This is, say, males. This is people with black hair, and they, unlike in the image space where these are all mixed up, these start to become decoupled or disentangled. And these are, you know, what we want to do. We want to move within this space to generate new faces. So there's a few contributions of this paper. What we're doing is we massively improve the efficiency by about 100 compared to StyleGAN, which means that because we're generating many more images that are exactly what we want, that means that we have improved the efficiency. We've also improved image diversity. So the original system was trained on Celeb A, which is basically attractive white people mostly. And we've want to produce people of a greater range, different ethnicities, wider pose, et cetera, et cetera. And this is this is from the Karras paper, and it shows how your real data might be distributed like so. You go to a latent space transformation and to produce a nice compact space where you can do sampling. And there's also what's called a W space, which is a transformation of that space, which improves the orthogonality of various attributes. So it improves the disentanglement of these properties. So what we've done here with Terry is we've taken this W latent space that's referred to in the Karras paper, and it looks like so, and we do some analysis in this space. In this case, it's just a simple PCA to find maximum components, and these components tend to correspond to attributes of interest. And then we do some resampling in that space. So we've got a space that's good, but it's not perceptually linear. So the resampling actually produces something that's more perceptually linear, which improves our ability to add diversity. And these are the sorts of faces we're generating. So when we generate these faces, we have a text translator, a little transformer up the front there, and says these are the sorts of faces I want. And it takes a random face or possibly a real face projection, and then can modify these faces according to these keywords. Okay, so we can get somebody, and the question is that we have for face recognition is, how do we know we're generating the same person? Because, you know, if we generate two faces, why would they're two random numbers, why would we know that they're the same person? So what we're doing is we're using ArcFace, which is a face recognition algorithm that's incredibly accurate, like 99.99 something %. And we're saying if the two people or the two synthesized images basically match each other according to arc face, we accept it's the same person. This is not a problem we have with normal photography in a photo booth, because with the person's in the booth and we take the photos, we know it's the same person all the time. We don't have the problem of identity. But in this case, we do, because each face is synthesized and we don't know if we've changed the identity. So we know roughly where identity belongs, and we try not to change that, but we change all these other things like hairstyles and so on to produce this diversity. And we use arc face to basically check that we haven't changed the identity too much. Okay. So, so it seems it's a bit funny to design a face recognition algorithm. We're actually using a face recognition algorithm, but you have the same problem with analyzing people from CCTV, because you see two people, you might think they're the same person, but maybe you're wrong. So you have this problem of knowing the identity. But you can also, once again, use a face recognition algorithm and then assume the algorithm's 100% correct, because it's about 99.99% correct, which is better than most humans. Okay, so there's a bunch of metrics there. I'm not talking about this paper, so I won't go through them, but basically we're getting quite good matches compared to the traditional style gown algorithm, so much improved accuracy. And if you look at the bottom, that's probably a big thing. For our method, to get the image that meets our specifications, it takes about 0.45 seconds per image, and it uses 1.189 gigabytes of well, this should be computing memory. For TeddyGAN, which is a strong competitor, it takes 35.68 seconds to generate an image, and it takes 5.567 gig of memory. And we've tried doing this synthesis as an ablation test using different latent spaces, including the one that we propose with the PCA, and basically we get much nicer synthesis when we use our space compared to the others. And so these are extreme cases. They don't look so realistic, because we're doing extreme changes to see which spaces look better. So you can see in these other spaces that have been proposed, generally with the same modification setting, we get bad looking images that start to look unrealistic, whereas in our Z space, we get very good quality images, despite the modifications. What is also interesting is that we can not only go from a random number in our latent space to a face, we can actually take a real person and find their space, their reconstruction in the latent space. So in this case, these are real people on the left, and we have converted them to from an image representation to a latent space representation. So basically, that is a conversion. You can see it's not the same photo, it's a latent space interpretation of that person. And then we can do the same modifications on a real person that we could do on a synthetic person, and we can take the reconstructed face, we can turn them from male to female. So we're doing I mean, there's a lot of that going on these days, and we can do it very fast. So no 18 months transition here, we can do it instantly. We can add eyeglasses to them. We can change them from a smiling face to a neutral face, change their hair color, give them a bit of a double chin. So we could take this face, reconstruct it, and then we could add blonde hair, arched eyebrows, mouth opening, pointy nose, old. And so we've got the possibility of doing face training on synthetic faces, and this is a little bit of a cheat perhaps, but we could actually take a real face from a real face database, do a reconstruction of it, and then do these transitions on it, and we would have a whole bunch of new faces that are based on real face prototypes, but they're so far away from the real face that they're basically, they're all synthetic. They're coming out of their synthetic system. So that's something we're contemplating as well. If we have trouble with fully synthetic faces, we could do a grounded face based on some real faces, but not use those real faces for training. So we can also add images together in this latent space, and you get semantically interesting images on the other side. So you can do sort of, you can do things like change lipstick and bangs, and you can add 5 o'clock shadow, etc., etc. So we're doing all these semantic manipulations, like semantic meaning meaningful manipulations in the image space. So we are already well down the track of going image synthesis via text, and this also uses transformers and so on for changing it. So this is one reason why stable diffusion is so exciting, because here it's producing artworks. So not just faces, but faces plus artsy objects. So, and I'm saying it's probably the greatest advance in deep learning since StyleGAN. The code is open sourced. So there were progenitors to StyleGAN, such as DALL-E 2, but they were commercial and they were not open sourced. So Stable Diffusion is more exciting because it's open source and we can get to play with it. These techniques are already commercial. Things like Jasper AI, Canva, and other companies will charge you money to use to run Stable Diffusion models. So Stable Diffusion is an open source alternative to DALL-E 2, and this is the sort of output you get from it. So when you can generate a whole bunch of images here. I'm not sure what the prompt was. So the prompt is the English text that's used to generate the image, and but the output looks like a stunningly beautiful graphic commercial art. Why is that? It's because it was trained on stunningly beautiful graphic commercial art. So it started with really attractive looking images, and so it produces attractive looking images. So there's always a bias from the training set. This is actually from a online. Now let's see. Okay, if you look at the bottom there, if you look at that link, that's a online description of Stable Diffusion. And so since I was doing this really quite quickly, I just took a few slides from there. So if you want to see the whole video, which is about 20 minutes, take a look at that. It's quite a nice explanation of Stable Diffusion. I'll just go through some highlights of those slides. So what is diffusion? Well, diffusion is a very simple forward process. What you do is you take an image and you add noise to it progressively until it's just noise and there's no image. So here we've got the forward diffusion process, which takes an image and converts it to noise. That's normally not what the sort of thing we want to do. We actually want to do the opposite of the forward diffusion process. We want to go from the noise and come back to an image. But if you go from an image to a noise, you don't have to guide it because it just becomes noise at the end. We have a clear sort of target, even though it's infinitely dimensional. But if you go from the noise back to the image, you have to guide it because you don't know which image you're going to produce. But that's exactly what we do. We do a backward diffusion process. And here we have a neural net, which is a form of a U-net, which is well known, and we'll talk about that later. And what it does is the opposite. It starts with the noise and comes back to an image. And we obviously have to guide that process. So we need a steering wheel or something to guide it in the right direction to make sure we get an image that looks nice. And so it doesn't do this in one step, it does it in multi-steps. So basically it estimates the noise and takes a little bit of the noise away from the noise pattern to start to reveal the image. And then it does run exactly the same algorithm again and take a little bit more noise off until you get back to a high quality image. So how do you run this? So in our backward diffusion process, each of these steps here is a neural net, which is a common format called a U-net. And the U-net looks like this. It's used in semantic segmentation and so on. And it basically has the input layers equal to the image and has a few layers there. And then it does a downsampling operation to some smaller layers. So this is a big image, the same size as our input image. And then we have a subsampled version, which is a quarter the number of pixels or half the lineal dimensions. And then it downsamples it again. And it comes down to a bottleneck layer, which is our latent representation, which obviously is low dimensionality. And then it upsamples. So you use neural upsampling to produce a bigger image and then a bigger image once again. So it's a downsampling step and an upsampling step. And it also has what are called skip connections between them. And these allow you to bypass these layers and jump directly from one layer to the other layer. So when you're training, if it's easier to do to bypass some of the neural network layers and jump, it will take the skip layer because that's will be used in preference. So it's a standard sort of architecture, and it follows the bottleneck principle. So what we say here is this is a whole image, and we convert that image to a low dimensional space which retains the semantics of this image. So instead of representing the pixels, it represents the idea of the image and or the semantics. And then from those semantics, it can just reverse the process and come back with a improved image. Now, these things are very easy to train because we start with an image, and to do generally training these, you start with an image and you reconstruct the image after going through the bottleneck layer. And so you don't have a problem of labeling and training. You just use a whole bunch of images. And the characteristics of this will depend upon what data set you use for training. Okay, so if we look at what happens between steps T and T-1, at step T, we have image, and we use the neural net to estimate the noise in the image. So theoretically, if you estimate the noise perfectly, we could take that noise off the image and come up with a clean image. But we don't do that because we need to use multiple steps so that we can steer the process. So if you've got if you want to do a maneuver with a car, it takes a while to turn the car around. You can't do you can't, for example, do a U-turn in your garage. You need a larger space. So with this as well, we also have say about 150 steps, so we have time to guide the process. And so here we have an image. Here is the estimate of the noise in the image, and then what we do is we subtract a percentage of this noise. So instead of subtracting all of the noise in one step, we subtract, say, 5% of the noise or something, and then we do the whole thing again. And the network, this network is the same for each layer. So there's only one train network. And we have to guide this process. And to guide this process, we have in parallel a natural language model. So we're using transformers, which came out of natural language modeling. And we have a coupling between the transformer model and this UNet. And so it guides the UNet towards what we want. So when you train this, you might say a silly looking dog is the word when we train this, and it will force this noisy image to go towards a silly looking dog. And if we train this enough with enough data and recommendations and so on, it actually can start synthesizing new images if we put in different prompts. Okay, so this is the paper for StyleGAN, for stable diffusion paper, and that was from Munich, and these guys have now been stolen by Heidelberg. So started out in Munich, and they demonstrated this technology on household objects like plates and human faces, because there's lots of databases like that, and could show how they could synthesize human faces and plates, which is perhaps not such a big deal, except they did do something there that made this method much faster. And what they did is they did everything in the latent space instead of the image space. Sorry, Stex, I'm probably a little bit over time. Is it okay, or should we wrap up quickly? No shake, so I'll keep going.
Yeah, just keep going. It's all good, thanks.
Yeah, it shouldn't be too long now. So this is just the principle. So they trained it on these images, which were basically plates and humans. And so if you typed a prompt in, they'd sort of tend to come out like plates and humans, which wasn't that exciting if you wanted to synthesize an astronaut sitting on a horse. So one of the big things that they did, which is actually a small thing from what I just told you, is instead of working in the image space, they decided to work in the latent space. So in the image space, what people would do is they tried to do high quality images, but the trouble with high quality images is with all this computation, it took a very, very long time to do the diffusion process. And so big images were difficult to do, so to put into the system, because they clogged the system up. And so what they then did is they used a downsampling method and an upsampling method to get this to work. So they basically they worked on either very small images, or they would turn big images into very small images, process them, and then use upsampling on the other side to produce a big high quality image. Okay, so but when they did this decoding, encoding, it was basically just downsampling and upsampling. What they did in this paper in August this year is they replaced downsampling with a typical DSP downsampler upsampler. They replaced that with a latent space downsampling. So as we said before, for the variational autoencoder, you can, instead of just doing making a big image a small image, you can make a big image something else, which is in the latent space, and you can't really represent it as an image anymore, but it's a small space that represents the semantics or the contents of the image. And the beauty of that is you can make that space more disentangled, so things that are meaningful start to become separate from each other. Whereas in the image, all the information is embedded in the same space. So so they could do high quality images by downsampling using a trained encoder into a latent space rather than an image space, and then they ran their UNet, and then they upsampled effectively within this. I shouldn't really call it upsampling, but it is sort of upsampling, but it's taking it from a small space to a big space, just like the variational autoencoder. So, if you know what's going on, that's not a big change. But what it did do is it meant they could synthesize very big images, and it also worked better because the space was somewhat disentangled and a better space for manipulation than the original image space. So, so what they're able to do with this is, so the big change was basically working in a latent space instead of an image space. And the other big change, which made it very exciting, is that they trained the system on artistic images. So people, when they want to produce an image, want a nice looking image. And what they did is they trained the system on a variety of nice looking images. And so with Stable Diffusion, you could describe a sort of image you want. And these are the sorts of images that could come out of Stable Diffusion. Very high res, very nice detailed images that match the input. And there's a comment here. It says, what makes this AI different is that it's explicitly trained on artwork from current working artists. So what they've done is taken the work of graphic artists who are very, very good at making nice images, and if you want to hire somebody to make a nice image for you, it'll cost you a lot of money. And so then they would generate images in the style of that artist. Because, obviously they got a bunch of things done by artistic people, and the copying is so extreme that it's actually, in saying this image, it's almost come up with the artist's signature through the latent diffusion. So that's how much it's tracked through. And so what it's actually stolen is the artist's ability to render an idea into a beautiful concept of art. And there's a lot of ethics complaints about this. So in the past, people have stolen from great artists like Van Gogh and from Monet and so on, and you can do art in the style of those artists. In this case, they used a lot of living artists, and some of those living artists have complained that now people can generate artwork as good as they would do just by writing some prompts in, and they can generate top quality commercial art. So that's pretty interesting. So I was just going to, I'll stop there at the ethics issues, and I think we'll hand on to our next speaker.
Yeah, thank you, Brian. That was really good. That really puts into context where Stable Diffusion, sort of fits in, which is precisely what we need for today, because our next speaker is going to go into slightly more technical details, and the speaker after that will go into the DDPM, which I can never remember what it is, but diffusion probabilistic models, which is the theory behind it all. But yeah, and CU's going to start off with, or follow on from Brian and talk about all of the technical model details are related to it. So you want this thing? I'll just get him hooked up.
Thank you.
He's just getting ready.
Your pocket, so I guess I just.
And I'll unpin Brian. Okay. Yep. And then I'll pin us. And that. There we go. Share your screen, huh? Oh no, you're doing it. Sorry. Okay, you already got it. Hopefully you can see the screen, and I'll pass it over to you. Thanks.
Thank you. So yeah, can everyone hear me? On Zoom. Is there a way to check? Okay, yeah, I can see the chat now. Okay, thank you. So I'll give a more technical introduction of what happens inside the diffusion model. But before that, I would like to show you the diffusion app actually available on Mac OS at the moment. They're making a Windows version, so it's called the Diffusion B. And you can just download the thing. It's going to download gigabytes of models, and you can just enter text prompt in here. Maybe we'll have a play later if we have time. But yeah, it does image to image, text to image, all that stuff. So it's crazy that it's already been packaged and distributed. You can use for free. And it works quite well on the new Apple silicons, which yeah, is not usually the case traditionally in deep learning. All right, so I'll just briefly talk about generative models in general. Usually when we talk about generative models, there are three metrics we're really interested in, right? So the first is the likelihood which means are we covering all the variations in the data set, or are we just covering a subset of it? And there's image quality as well. So is the resolution good? Do we have sufficient details? And the speed, how fast can the model generate images? And we have GANs as the first class of algorithms to effectively generate images, and they generate pretty detailed images at high resolution, especially after a lot of iterations of improvements. And they are really fast because all we do is a forward pass on some noise, right? And it's going to give us an image immediately. But the problem is that they don't usually cover the full distribution. Sometimes the real distribution could be that large and it'll just learn a skewed subset of it. So that's why you can see failure cases quite frequently with GANs. And there are VAEs as well. They sort of trade image quality for more coverage of image variations. So when you train VAEs, you might see more varied images, a more smoother latent space, but they tend to be blurry. And now we have diffusion now. Let me just close that window. Okay, so now we have diffusion models, which sort of does really well in terms of likelihood, variation, image quality, but yeah, it sacrifices a little bit of speed. But that sacrifice is not significant enough to hamper any real life applications. And we'll see that stable diffusion actually make a major step towards speeding up these models. So yeah, these are just some results from the stable diffusion model. As you can see, due to those likelihood and image quality attributes, we can generate really diverse images and condition them on these really abstract conditioning, right? Like text, it needs to understand what's in text and generate things based on that. But the technology that drives that is just this very simple diffusion process. So let's just break it down now. Given a data set, there are two processes that we can perform in the diffusion model. So the first is called the iterative forward noising process, in which over maybe 1,000 steps, let's say that from x0 to x1000, we gradually add noise. We add a little bit of noise at a time until we completely destroy the noise. So in the end, we'll end up with completely random normal noise. We call that the Q process. So that's the forward iterative process. And with that process in mind, we can just create a new generative model by just reversing that process, right? Because now we can just start with random noise and gradually denoise, reverse every step of the forward process to arrive at a clean image. And naturally, neural nets are really good at generating images based on images, right? So we can just have an iterative neural net that takes in a slightly more noisy image and try to produce a cleaner image. And we do that over, at least originally, over 1,000 steps until we clean up the image completely. So before we go more into the neural net bit, I'll just talk a bit more about the forward process, which is the process we use to generate the training data, the noisy images. So it's controlled by this scheduling factor or scheduling constant that changes according to each time step. And as you can see, each step of the forward process gives us a normal distribution, and the mean values are the image values, or the image pixel. That's the signal, and the variance is the noise we introduce. And it has that beta t parameter in it that increases as t increases. What that means is from left to right, beta t increases. And let's graph what that does as beta t increases. So as beta t increases, the noise factor increases, right? So we introduce more and more noise with time. And the 1 minus beta t square root, it reduces. So it decreases over time. So we end up with less and less image signal. I've made a little animation here by just repeating that equation, that recursive equation. And you can see when t reaches 1000, beta t reaches 0.02, which is the upper bound, we do gradually approach a normal distribution. So mean becomes 0, standard deviation becomes 1. So we just use those images for training. But there's a problem now with that process is if we want to generate an arbitrary noisy image, let's say X999, we have to go through 999 noising steps, right, iteratively from a clean image. And that's going to take a lot of time if we were to sample a batch of 128 images, right? So we have to do that recursion over and over again. And there is actually a way to speed that up in the diffusion literature, is we create this value, derived value alpha t based on beta t. Then we just store some intermediate values of the alpha t. So specifically what we store is the cumulative product of the alpha values, right? So from the first entry to the 1000th time step, we just store those 1000 values, and we can use those stored values to create any time step on the go, right? So if you need xt, or if t equals 999, we can arrive at that with just x0, sorry, that's the clean image. So we just combine the clean image with some noise and using our stored value to fuse them together. Okay, so that's how we create the training data. Now let's see the diffusion process, which uses a U-net-like architecture. Okay, so the neural net does something very simple. So it just takes in a noisy image and try to produce a less noisy version of the image. There are more details which I'll talk about later, but the things to take note is that it is an encoder-decoder architecture, right? A U-net-like architecture, and they use a little bit of self-attention in this model because I guess attention is just very powerful in any model in general. And it also injects the time point information. I guess it just gives the diffusion model a little bit of a notion of which time step it's at and how much noise to remove. And in theory, the model should predict the mean and the variance of the slightly more denoised image, but in the first literature, at least, they fix the variance, and we'll see how that comes into play. But now we're just predicting the pixel values, the mean values of the denoised image. And there is a little bit of more technical details. That's not actually what happens in practice, even though that's our objective, but in practice, the math actually works out to be something different. In practice, we're actually predicting the noise directly. So what that means is, given that image, we make the neural net predict how much noise was added. So that's the total noise. And with total noise, we can recover the clean image by just subtracting the noise from the noisy image, right? And in practice, it's not going to give us a clean image in one step. We still have to do the 1000 step iterative forward, iterative diffusion, denoising process. But that's the learning objective, because we know how much noise we applied when we generate the data, we can just compute the loss. So it could be MSE loss or L1 loss. And yeah, that turns out to be the loss function that gives us the images we generate. And the reason we use the loss function over noise is because the math actually breaks down into that. So here we have the negative log likelihood loss, which I'm not going to go into too much detail. So that just maximizes the likelihood of the training data, right? And that loss itself is not directly computable, so it's not tractable. So we use a surrogate loss that we can minimize instead. And that surrogate loss function, after a lot of manipulation and substitution, breaks down into that term. So you can see that is just epsilon. Here is the noise. We're just computing a loss over noise. So that's a very important detail, at least for now. We are computing loss over noise. And let's look at the training a little bit more formally. As you can see here, So that's the training loop, right? So we're just sampling a batch of random noisy images, which we can generate using the alpha T value we've stored. And we just feed that into the neural net. Theta, so theta is here, represent the weights, right? And epsilon theta is just the predicted noise, how much noise the neural net thinks is in the image. And the loss is the noise loss. Okay, so for sampling, we use a slightly different process. During inference time, we start with a completely random normal noise image, right? So that's n and 0 and 1. And for each time step, we still predict the noise. So you see the epsilon theta here, and that noise gets taken from, gets subtracted from the image itself every time. So we just keep iterating from t equals 1000 to t equals 1 until we clean up the image. And these scaling factors, the alpha T scaling factors, are just from rearranging the equation from these previous terms, and you can see that in the paper in more detail. But yeah, that's the intuition here. And here we have a little bit of noise we add each time as well in the sampling process. And as I've said, we are not modeling the variance at this point. We're using a fixed one. So we're predefine sigma T variance. We just sample that. And of course, in the later diffusion papers, they've proposed ways to model the variance as well. So originally, the UNet just predicts the RGB values of the image, right? So that's the mean. Here, it predicts 3 additional channels. So just represent the variance of the RGB values. And it has this additional loss term as well for the variance. So this is the noise loss we've got before for the mean, but now we have additional variational lower bound loss for the variance. But yeah, you can see that in the paper in more detail. This is not overly important because it is not like a groundbreaking discovery in the diffusion literature. They just achieved a little bit better empirical results. And the training loop is very similar. It's just we have that additional loss function on top of the noise loss function, right? And the sampling process is pretty much the same, except we have learned or a predicted variance V rather than a predefined sigma. Okay, so now I'll just talk about some more influential changes, which is, as we've seen, stable diffusion, which is based on this work called latent diffusion. And its biggest contribution, at least from the start, is the ability to generate high resolution images. So as we've seen before, high resolution images are really hard to generate because the model needs to focus on generating all of those details, which can be quite overwhelming, right? And what stable diffusion or latent diffusion does is it compresses the image to a lower dimensional space. And we use autoencoder to do that. So autoencoders are really good at compressing data and reconstructing data. And this way, we make sure that the latent space is only responsible for what's essential, which is the semantics of the image. And the autoencoder, which are CNNs, can take care of the perceptual details. So as a result, we can just operate a diffusion model in the latent space, which is fairly low resolution and a lot easier to train. And there are some requirements for this autoencoder. The first of all, it's a fully convolutional neural net. So you may have played with autoencoders with a vector as the latent space, right? So you use some dense layer in the middle to compress it down to vector space. And that's not what we're doing here because we're trying to preserve the image integrity. So we still keep the spatial information. The second is it's very heavily regularized. So if we just train a naive autoencoder, it's going to have distributions all over the place. It's very hard to interface another model like a diffusion model in the middle. So what they did is we can just have a KL divergence loss function here to make sure that the latent space is more not uniform, is more normally distributed. And another way to do it, or a better way empirically, is using vector quantization. So you can look that up later, but I'm not going to go into too much detail here. What that does is it just turns the latent space into discrete vectors. So basically that makes it easier to interface with the diffusion model. And another detail is that there are GAN loss functions and the perceptual loss functions used to train this autoencoder, which is not very conventional. And the reason we use GAN loss is so the model can make up details rather than just using this traditional MSE loss, which usually results in blurry images. Okay, let's see that with these additional components, how does the diffusion pipeline work? So we still have these images, right? From a clear image to a complete destruction of the image. And we just map all of them to the latent space. Then we just run the diffusion process as is. Then later we can just decode the image using the trained decoder to get the high resolution image. So it's a very elegant idea. I guess sometimes the best ideas are usually the most elegant. And as you can see, I guess what I'm trying to get at here is how varied the results can be. So especially this one, generating images directly from ImageNet. ImageNet has a lot of objects and models can usually get confused and mix up objects. But as you can see with latent diffusion, it sort of still generates complete objects that make semantic sense. And another thing that's really important, or the highlight of stable diffusion, is really the conditioning. So we've seen that we can condition the entire model on text, right? So text basically comes in here and goes through some transformers, because that's always the case. And and gets injected into the model using attention. And what I think is the key success of stable diffusion is how everything gets injected into this lower dimensional latent space. So this model here controls the semantics of the image. And the encoder decoder here is what worries about the trivial details of the image. Right, so you can think of the success as really operating in latent space. And of course, we can use some other types of conditioning as well, like entire images. So we can generate image to image translation, and that just gets concatenated to the input. So yeah, multiple conditionings are possible with stable diffusion and latent diffusion. So now I just talk about another very important finding recently. So this paper, I'm pretty sure it's still in peer review, but it already has a pretty significant impact. So they make us rethink the idea of diffusion or the framework itself. They start out by observing that throughout all of the theory and process, there is always this little noise here, but it always assumes noise is a most important component of the diffusion model. But can we replace it with something else? Is the real diffusion model more general than that? And they found that it is indeed the case. So up the top here, so that is just the traditional diffusion model, right? So it does the noising and denoising using a network. And we can actually replace that with any process possible. So it no longer has to be this N. So it seems to be the case that the theory just completely breaks down and we can learn everything with neural nets. And yeah, we can have blurring and we can even stack another image on top and we can block out pixels and we can do downsampling and we can do this snow effect. So a model is always able to recover images or generate images from this destruction of images. Okay, but there is one minor detail. So using the traditional sampling process, these methods down here will not work well. So they only work with noise. So they proposed a new sampling process. So up the top here, we have the traditional sampling process, which they found when applied to things other than noise can lead to catastrophic changes that throw off the rest of the process. And what they did was they proposed a new sampling process with some more factors, some more regularization, so that the changes are more mild at each time step. But with that change, we can use any process, any transformation. And they've also proven by induction that this process eventually becomes independent of our transformation. So that sort of explains why we can just have any transformation possible. So it opens the door of, okay, what transformation can we design? Because noise itself might not make sense in all application areas. Could there be transformations that make more sense for the application? Okay, so that's pretty much the content. I'll just give a quick conclusion. So diffusion models usually, when they start out, have pretty rigorous mathematical formulation, but I guess with the introduction of the code diffusion paper, it really makes us rethink how much can we learn and how much can we mathematically model. And they can generate really high quality images while capturing most of the modes in the data, and the speed sacrifice is pretty okay. And they are a lot easier to train, at least from my experience, when compared to GANs. As the stable diffusion model with the VQVAE as the encoder decoder trains within a few hours compared to a few days if we were training a GAN. And as you can see, diffusion literature goes really, really fast. So yeah, it's we have to constantly keep updated to keep up. So yeah, that's my talk. Any questions?
Yeah, so thanks to you. That was really, really informative. The cold diffusion stuff is going to be also another major change to the diffusion stuff. I have some quick questions. Yeah, so you would have, so the model actually predicts the actual noise. So that's it.
Yes.
It sort of outputs it outputs noise.
Yes.
It's kind of counterintuitive to me because noise really doesn't have much information in it to begin with.
Yes.
So how can a neural network predict noise to such accuracy that you can actually, you end up, I guess it's not going to be super accurate because that's why you need to do it 1,000 times.
Yeah.
But it's accurate enough so that it does do some denoising. So usually when you have a denoising model, you kind of think of it as learning the stuff that's not noise, and it tries to recover that image. That's why it becomes blurry. Do you have any feeling for why this works?
I guess the first thing is the noise is already in the image. So I guess it just needs to identify the according to the contrast and stuff. But the iterative process is very important because if we just pass it through once, it's going to be pretty bad. Or if we do it through over 1,000 times, we can just create something every time, not perfect, but fix it the next time. Yes, that's what's happening, at least practically.
Yeah, so there's a new paper by, I think, DeepMind, or was it Google Brain? I always get confused. In NIPS, which basically now they can do, using model distillation, do it in 4 steps. So you don't need 1,000 steps anymore. You can just do it in 4 steps, which is another big change. But anyway, yeah, so I'll guess I'll leave my other questions later. I'll open it up to the floor for any questions. In person. Yep.
Yeah. I mean, your comment about noise and images, I mean, you are biased towards what we call images because you're a human being. You know, mathematically, the pixel distributions of the noise sample and the image sample are identical. There's no difference between, you know, you call it noise, which has semantic meaning to you, but it's just another set of pixel values. So it's not actually predicting the noise. It's basically saying, I think this is the image I'm trying to build, and if that were the image I'm aiming for, then this is what the noise is. So it's quite, you know, so it's not like it's predicting something random. It's no longer a random sample. It's basically the error from the image you think it is, you know, when you're reconstructing. So I think as humans, naturally, we get a little bit biased because, as I said, we're much more interested in things that are semantically meaningful than things that aren't semantically meaningful, and so we think the noise is somehow different, but it's just another set of samples, you know.
Yep. No, thanks. That's helpful. Yeah. So the other point, CU, is if you go back to where you started having, you know, you store all of these noise so you can produce them at any time you like.
Yes. Yep.
Yeah, so that alpha there. So, but once you, is alpha like a fixed level of noise? Is that what that is?
I guess you can think of it because beta T is the schedule, right? And alpha T is you write directly from beta T.
Yeah.
We're just storing those values for each time step. Each time step has a different constant.
So in a way, you are actually, you have a set level of noise at every,
Yes.
as the neural network is learning to remove the set level of noise.
Yes. So yeah, a set level of noise versus the original image signal.
Right.
So yeah.
I wonder if it gets more, it gets better or worse if that's actually noise. It's like changes all the time. Has anyone done that? Do you know?
I'm not sure, but I
mean,
think they kicked that value just because when we reach T equals 1000, so it actually for all images it converges to random noise. So
Yeah, so the way you do forward processing in this DDPM paper, so they actually fix the noise for all the steps and directly go to step 100, for example. So Shix is asking if you actually go 100 steps, at each step you add a real random noise, like each step is different. Would that make a difference or not? Is that right?
Does that, how does that correspond to the maths? Like, so practically I can understand.
yeah,
It makes a lot of sense. You pre-cache the noise so you don't have to compute it all the time. But is that a little bit of cheating? Are you actually following the theory there, or are you just learning the fixed noise?
it is cheating, but I think it's based on the math as well. Like it should be equivalent.
Right.
Like using beta T and this stored alpha T. I think there's a math derivation that shows.
Shakes,
Yep.
that cheating step is based on the assumption using Gaussian noise. And if you add two Gaussian noise sources, they become Gaussian noise, which is not true for all other distributions of noise. So if you use Gaussian noise, then you can do all those steps in one step mathematically using central limits theorem.
Yeah. But my point is that those individual, you've fixed them. So you've pre-sampled the Gaussian noise. And so you've stored those pre-sampled Gaussian noise distributions. And then you are actually, so your network could memorize the noise, is my point, because it's not random. It's random in the beginning. And then you learn the model, but the model will then, the model is kind of, could potentially memorize how to remove the noise all the time.
Well, it's meant to memorize the noise. That's why you give it the time step. The time step is basically tells it you're expecting this level of noise. You're expecting this, variance and so on, because you know which time.
Yep.
And I guess during training, noise is sampled on the bill as well. So for each new training step, there's a new noise. So that's the actual.
Right. Okay. So it changes every epoch or every iteration.
Yeah, it's every step, I guess. So for every sample, every training step will be a different set of pixels. Same distribution, but different.
Yeah. Okay. Right. So you're pre-caching it quite regularly. So you are. Yeah. Okay.
Yeah. So what we're caching here is actually just the constants or the mixing factors, alpha T. So that still get sampled each time. So we're just caching the. We're just caching the mixing factors.
Oh, okay, right. Yep. Oh, okay, cool. All right, I think that clears up a concern I had, but now, yeah, it's a lot better. Sorry, I've hogged the questions enough. There's one in the chat, I think there. Is there a comment or a...
So yeah, Karen has a question. So do I have an insight why DDPMs should be better than VAEs or GANs intuitively? So intuitively speaking, I would say that breaking down of a problem from a one-step process to 1,000 steps usually result in better results. I guess from the autoregressive models I've trained, it usually matches the distribution more closely. But yeah, it's just my intuition.
Yeah, GANs don't really model the real distribution, do
No,
they?
they
It's
don't.
like a skewed.
Yeah.
So that's another good reason.
Yeah.
Yes,
Well,
yeah,
GANs are known to have more holes in their representation space than VAEs, because there's not an explicit loss function forcing the output to be contiguous. So so GANs, if you move around in GAN, and that's one of the problems with style GAN. If you move around in style GAN space, you can reach regions which aren't reasonably faces, which with the VAE for the MNIST and so on. I mean, everything is a reasonable handwritten digit. So GANs are known to have that sort of problem. So if you when you're doing modifications, you can get into non-viable spaces and basically holes in the manifold.
Yep. Yeah, so I guess the VQ VAE is a kind of a good, if you're trying to be accurate and have a proper manifold, is a good option. But I guess these things are becoming so big now, they're all just one. They're just one big thing, because that kind of has a VQ VAE in the middle with a transformer plus some GAN losses. It's kind of putting together everything we have.
Yeah, and I think another thing about diffusion is we are sacrificing something for the nice qualities. We're actually sacrificing speed. So yeah, they are not always the best choice. In some applications, GANs will still be viable, like real-time videos. For diffusion, we still have a long way to go. We're sacrificing so much speed.
So what's the inference time for stable diffusion?
So it depends on the machine, but on this Apple machine with GPU support, it's still 20 seconds per image, which is not horrible, but not real time.
Yeah, GAN.
Well, yeah,
GANs are probably like less than a second.
On NVIDIA GPU, it might be 10 seconds, 5 seconds.
I think it really depends upon the synthesis size. I mean, obviously, the speed will depend upon how many pixels you're generating.
Yeah.
So to some extent, but this idea, I mean, I think it's interesting coming from an image processing background, where if you have images, if you want to make them smaller or larger, there's just one way to do it, pretty much. And this idea of using perceptual compression and so on is incredibly powerful, especially when you can basically do upsampling of images, and the upsampling of images using DSP usually gives you a lot of blurring and various things, and whereas if you do it from these perceptual spaces, you can upsample and resize things, and there's none of these blurring problems. It's really I think quite an advance in I suppose traditional image processing to be used neural perceptual interpolation. Yeah,
that was my next question to you. I guess to Brian as well, and Hong Fu here as well, or anyone who's sort of in this sort of space, is I guess the idea that we could now probably do all of our research in whatever application that we're applying these models to in latent space.
Yeah, what's interesting is there's no standard latent space. They're all trained latent spaces, whereas it's like with image compression algorithms, there are all these different algorithms, but there's no standard one. It seems to me that a logical step is to wind up with a standard perceptual space, so you can recode images into this space and then resize them at all different sizes, which is really important in a modern internet, where depending upon which device you've got, you need different numbers of pixels. And this is one of the if you look at say H.265, H.264, it's a scalable architecture so that you can take CCTV video, for example, and make it high res, low res, and even TV sets now. I've got a 4K TV, but older TVs are 2K. In a standard definition was 0.3 of a K. And you've got the same movie and you want to show it on all those devices, fully exploiting the quality of the devices. So I think there's room there for a standard, rather than something that represents all imagery, like JPEG, but doing it in this neural perceptual space.
Yeah. So I mean, from our medical imaging spaces, like we do segmentation and other tasks, we could probably now do it in latent space just as effectively, and then upsample and really be able to use smaller hardware and all those sorts of things, which is really cool.
Yeah, I think so, because there's obviously huge advantages in putting things into a latent space. See, JPEG was done using traditional image processing techniques, and then they had perceptual people looking at the images, using different compression levels and saying, this is really nice, this is not very nice. And, so they were sort of designed to be perceptually linear, I suppose you'd say. I'm not sure if that's the right word, but you know what I mean. It was designed for photographic images, and it wasn't trained on photographic images. Basically, it was tested, heavily tested on traditional snapshots and photographic images. So it's not based on signal to noise ratio or some objective. It's still perceptual, but this seems so much more powerful.
Yep.
And it's an obvious step. Instead of using traditional image resampling, even neural resampling, go to a latent space that's has some semantic meaning.
Yep.
And,
So, see, you want to show your thing, what you were going to
It'd be
show.
good if I could put something in a latent space and you could reinterpret it. Because if everyone trains their own, there's no possibility of exchange at the latent level, which is a very useful compressed level of images.
Yeah.
Okay. And there's a question from Boya as well. Is it similar to the reparameterization in VAEs? I'm not too sure if there's. I don't think there is a reparameterization. This.
Yeah, I'm not sure. Say you want to do your demo, and then we'll move on to the next talk. Thanks.
I'll say a problem with using neural interpretation of images rather than using traditional DSP is there's a possibility of it going terribly wrong.
Yeah, hallucination and
Yeah, you basically, you do the conversion, and for certain images, it might just reconstruct it in a terribly wrong way. And there's a whole bunch of literature that I've just become familiar with on out of distribution testing, where this is the problem. If you test and train on data from basically the same data set, that's the way most people do things. They just break it into two, randomize it, break it into two sets and test it, but it doesn't test the pathological cases. And out of distribution testing is sort of like what you need for a driving car. Imagine you've got a self-driving car and you're driving around in that car, and there's a baby lying on the road in front of you. What is it going to do? What do you think? What should it do? I mean, this is the problem. When you see something that's totally outside the training set, you have no idea what it's going to do.
yeah, I think in the School of Psychology and Business School, they've been looking at where are those important? Are those human factors important? Obviously, the self-driving car, they will be important. And
well, it's sort of the suggestion that the paradigm of test and train, which is well used and is a good starting point, is not sufficient for testing stuff to work in the real world. Like, because you'll encounter things that you could never train for, you could never anticipate the training set, and you want a reasonable behavior given totally unknown data. And it's one thing if you test it and train it and just publish it in CVPR. It's a different thing if you're in the car and there's a baby in front of you.
Yeah.
Because it has to work under extreme circumstances. A bit like, that Boeing jet that they said something, if one of those sensors went wrong or something, it went into a crash dive for the 737.
Yeah.
So you don't want that to happen, especially if you're in that 737.
Yep.
And that's a barrier. If you don't have a good test protocol, you can never really trust these things in the real world.
Yep, there's plenty of opportunities there.
Yeah, but I mean, because of its huge advantages, you obviously want to use these. But so it's interesting. So that the train and test paradigm seems to have been changed around with this out of distribution testing. So basically, you do train and test, and then you have to start looking at out of distribution testing. It's closely related to adversarial attacks.
Yeah. Yep. Yeah. So hopefully, us as researchers, we don't have to worry too much about that, and that's an opportunity for the next set of developers. All right, I think we'll move on to the next talk, which we hopefully get some more insights on what's actually going on. So Christina, if she's there, yes.
Yeah, I'm here. Hello, Shakespeare.
Hi.
Hi.
Yeah, so I'll just try to. Am I still pinned? Yeah, I'm pinned. I'll remove the pin. There we go. Excellent. Yeah, so whenever you're ready, if you can share your screen. So Christina is a student working with me, and she's been using diffusion models for a bit now. And she's going to give a talk on, yeah, DDPMs. All right, Christina, whenever you're ready, go for it. Thanks.
Okay. Yeah. So first I will introduce some background, and then I will introduce the diffusion-based generative model theory. So first of all, we usually use the generative model to sample the new data point. So first we learn a model to represent the probability distribution of the data point, and then we use a model to generate new samples. So GANs we are familiar with. However, it learns the implicit density of the data distribution. And so, and VAE, it learns the explicit density, but it just approximates density, not the exact density. So VAE is just a likelihood-based model. So it can learn the probability density by maximize the likelihood. However, it requires special architecture or surrogate losses to deal with the intractable partition function. And for GANs, although it has a better quality of samples, however, it requires adversarial training, which will lead to unstable and model collapse during training. So here is diffusion model. It defines a Markov chain of diffusion process, which gradually add the Gaussian noise, and then it learned to reverse the diffusion process to construct desirable data sample from the noise. And unlike VAE, the diffusion model are learned with a fixed procedure, and the latent variable has high dimension. So I will go through the theory of the diffusion model. First of all, I will introduce the score-based model. How to represent a probability distribution of data sets. We know that the probability distribution of data set has the intractable normalizing constant. So to avoid to this part, we can estimate the gradient of the probability density. So here is the score function. We can see that the score is a vector field, and it points to the direction where the log data density grows the most. So the objective is we use the neural network to learn the score function. The challenge is that we don't know the exact true data distribution. So instead of learn the true distribution, we can learn the denoising score. So we use the denoising score matching method. It estimates the score of perturbed data distribution. So here is the objective function. The advantage of this is that this perturbed data distribution is easily to compute, and it can scale to high dimensional data more efficient. And after learning the score function, we can use a Latent dynamic sampling to sample new data points. And the procedure is that first we initial the chain from the priority distribution, and then we update the procedure following this formula. By the score function we have learned before. So, however, it has some disadvantage. One is that it is inaccurate when the data density is very low. And second is that the score estimate is undefined and inconsistent when the data reside on a very low dimension manifold. And third is that it cannot support the data distribution, which is has two joint model. For example, if the data distribution is a weighted average of two distribution. This method cannot learn the weights of. So the solution is we perturb the data with various level of Gaussian noise. This noise conditional score network can estimate score corresponding to all score levels. By adding the noise, we can see that the distribution can fill up the space. So by learning the score function, we can get the true data distribution. So we can use a nailed Langevin dynamic sample. It follows the two steps. It runs a Langevin dynamic for different scale of noise in sequence, and for the next iteration, it uses the final sample of the last iteration as initialization of the next sample. So we can see from the results, it can learn the relationship between the two different distribution. So before I introduce the variational diffusion model, I will introduce the hierarchy VAE. Hierarchy VAE is a generalization of a VAE. The latent variables are generated from higher level of latence. And Markov hierarchy VAE is a generative process modeled as Markov chain. We can see that in each steps, the latent is learned from its previous only related with its previous latent space. So based on this, we get the joint distribution and posterior of the Markov hierarchy VAE, and we also can get the evidence lower bound of the Markov hierarchy VAE. You can see as the stack of several VAE. So for variation diffusion model, it just we can see start from the Markov hierarchy VAE. It has three additional restrictions. The first one is that the latency dimension is exactly equals to the data dimension. And the second restriction is the structure of the latent encoder is not learned. It is predefined as a linear Gaussian model. So, and the third one is the Gaussian parameter of the latent encoder vary over time. So in such way, the distribution of latent at final time step t is a standard Gaussian. So based on the first restriction, we can get the VDM posterior, and based on the second restriction, the encoder transaction can be seen as a Gaussian Gaussian distribution, and based on the third restriction, the joint distribution is can written as this. And by Bayesian rules and Markov property, we can rewritten the encoder process like this. So the VAE can be optimized by maximize the evidence lower bound. So we can see that it consists of three terms. The first term is reconstruction term. It predicts the log probability of original image given the first step of the latent. And second term is priori matching term. It minimizes final latent distribution with a Gaussian priori. And the third term is denoising matching term. It learns which requires that we will learn the desirable denoising transaction step as approximate to ground truth denoising transaction step. Here is the neural network we want to learn. It is a denoising transaction step, and here is a ground truth denoising transaction step. And it can be written as KL divergence. To optimize, so two solutions. Every forward process, because every forward process is a Gaussian transformation, so we can rewrite the xt as a function of x0. And the Gaussian form of denoising step is follow this formula. So we can have the mu q and the standard deviation of the Gaussian distribution. So based on this formula, because every KL term compares to Gaussian distribution, so to optimize to get the solution, we can minimize the mean of the two distribution. So here is the denoising matching term. We can minimize the mu theta with a true distribution. Here are three equivalent interpretation of this formula. The first one is we can predict the original image. We can see that the q, the mu q is a function of xt and t, and mu theta is the neural net we want to learn. So in this case, xt theta is parametered by the neural network to predict x0 from noisy image at xt. So in this case, we can learn a neural network to predict the original image from its noisy version. And the second interpretation is that we can predict the source noise. We can rewrite the original image with the source noise and xt. So we can transfer the formula into this one. So if epsilon theta is a neural network, so in this case, we learn a neural network to learn to predict the noise. And the third interpolation is to predict score function. This formula is based on Twindy's formula. So after the transformation, we can see that we can learn the neural network to learn the score function. Here, I want to introduce the relationship between the score function and the source noise. We know that by learning the score function, we can move the data in the data space to maximize the log probability. And by adding source noise to the data, we just move this data to its opposite direction of denoising the image. So modeling the score function is equivalent to modeling the negative of source noise. And finally, I want to introduce a unified framework. Consider the diffusion process as continuous time scattered stochastic process. We can transform the diffusion process from discrete time to continuous time. And many stochastic process are solutions of SDE, which is statistic differential equations. And SDE process is following this form. And FT is the drifting coefficient. The solution of SDE is a continuous collection of random variable which trace a stochastic trajectory. So the reverse for the reverse process, we can reverse a perturbance process for sampling data by using reverse SDE, and the reverse SDE is following this form, and this is a score function we need to learn. For sampling, and the relationship between NCSN and DDPM and the SDE is that NCSN is variance exploring SDE, and DDPM is just variance preserved SDE. After training the neural network, we can estimate the score function with the numerical SDE solver, and linear Maruyama method is the easiest to numerical SDE solver. First, it's discrete SDE using finite time steps, and then it updates X by following these two steps. It chooses a small negative time step and iterates the X using this formula. Here is a predictor and corrector sampling method. In this method, the predictor is numerical SDE solver. It can predict xt plus delta t based on the existing sample xt during each time steps. And the corrector is using MC method procedure that relies on the score function. So in each iteration, it first predicts the xt based on the previous step, and then correct the and then using corrector to move the predict one to its highest probability. So by using this method, it can improve the sample quality and get a higher quality sampling. And finally, I will introduce the probability flow ODE. It is a deterministic process that shares the same range probability density as the SDE. It has several advantages. First of all, because it is determined process, so it can exactly get the likelihood of the data distribution. And the second, if we use black box ODE solver, we can get a more efficient sampler. We can see from this figure. By using the second order ODE solver, it can provide excellent trade-off between the transaction error and NFE. We can see the red line, the UC second order ODE solver. It can get a lower FID score image by using few steps compared to the SDE. And by carefully design the ODE schedule, they can also reduce the transaction error, which means that we can have a higher, we can have a lower NLL score compared to SDE. And because it is a deterministic process, so we can manipulate the latent space. Here is examples. We can interpolate the latent space or reduce the normal of embedding space. And finally, it is unique identifiable encoding. So we can see that the VAE will map the data to the latent space. If we train two model or two VAEs, it will map the data to the latent space into 2 points. And if we train an ODE model, this 2 model will map the same data points to the same point in the latent space. And here is its value. We can see the model 1 and model 2 are very close to each other. Here is a theory of the diffusion-based model. Thank you.
I was muted. Thanks, Christina. That's a great job explaining that, because that's a very dense mathematical framework. And I think you got most of it across. I didn't get most of it, but it probably requires further reading from our side. So well done. I can probably summarize it a little bit from me, and maybe yourself or others can correct me. So I can see that, I don't know if you can let me unpin stuff. There we go. From me, I can see that you've got the Langevin process, which is why you need to add different levels of noise. You've got that.
Yeah.
14, slide 14. So that's the first step. That's the first step of the diffusion model, where you need to add different levels of noise. And then to handle how to add the noise and to denoise it, you have these hierarchical VAEs for each level of noise, which that gives you with the Markov chain. So that gives you the iterative network.
Yes.
And then your diffusion VAEs are the ones that actually implement. Yeah, that's it. So it implements that chain across many iterations to basically estimate the noise.
Yes.
So you can
As
see
you said,
there.
yeah, the noise is predefined. It is a predefined linear Gaussian process. Yeah.
Yeah. And then, yeah, so I think your talk answered a lot of my questions I had with after CU's talk, because there's the other step where you talk about how you can take the Gaussian of, if you do with what Brian mentioned, if you have, I think there's a little slide where you sort of, the parameters match. If you have two Gaussians, if you can do them, you can simplify the equation to get like a estimate. Where is it?
Yes.
Anyway, so I had that
I
question.
minimize the mean of the true distribution. Yeah.
Yeah.
Because the standard deviation, if we treat the Gaussian noise as the predefined one, so we can calculate the standard deviation by the fixed procedure. So we don't need to don't need to learn the standard deviation. We just need to learn the mean of the true distribution.
Yeah. Yep, no, great. Are there any other questions from the audience or from Zoom? You got a question from the audience?
I just have a general question. So it seems like there are the score-based models and also diffusion models, and even though Song Yang's paper, they've shown that how they relate to each other, but still I feel like these are two branches that people use, either use score-based or use diffusion. So do you have any idea like which one works better in terms of implementation for applications, and why diffusion is getting much more popular than the score-based one, it seems like?
Great question.
Yeah, so we can see from these three interpolations, there are some relationship between the DDPM and the score-based model. So here the loss function shown here is always using the DDPM. They learns neural network to predict the noise, and the third interpolation is the score-based one. And for the applications, I think the DDPM is easier to learn, to make the neural network to learn the noise. So I think the DDPM is more popular than the score-based one.
Okay.
Is it because it's easy to train and learn?
Is it easier to train and learn, Hongfu says? Is that why diffusion?
Yeah, I think so. It's easier to learn because we can get the mu and mu at each step, each time step, because we can calculate using some formula, and And the code in the DDPM is also use the formula in their paper to get the new get the predictor get the noise they want to predict to train the neural network. And I think it's easier to train the neural network by using this formula compared to the score-based model.
All right. Okay, we're kind of running out of time. So, I mean, we'll keep going. So although we might go over the time limit, we'll just keep going on our regular thing. It's all being recorded. So that should be okay. Thanks, Christina, for your talk. We will now move on to Wei. And Wei has actually submitted some work applying diffusion models to imaging. And Wei is Hong Fu's student. Hong Fu is a DECRA fellow here at the school. Is it now a senior research fellow or a senior lecturer, or what is it at the moment? Senior research fellow, excellent, awesome, that's amazing. So Wei, whenever you're ready, did you want to come here? You stand here or?
Yeah.
Oh, yeah, sure. Well, can everyone see you?
Yeah.
Okay, cool. So yeah, we'll pass it on to Wei, thanks. Can you hear Wei? I'm not sure. We can't see you. Do you want to turn on your camera? Do you have a camera?
Yeah. So can you turn this on?
Oh, yeah.
Yeah.
How about now?
Can you hear me? Yeah, okay, let's start. Let me first introduce some background of diffusion models. I will give some intuition of the diffusion models. And the figure shows the diffusion and denoising process of a diffusion model called DDPM. And given sufficient data and model capacity, the diffusion model can learn a reverse process similar to the forward process. In other words, DDPM can learn a marginal distribution similar to the forward process at each time step. For simplicity, we assume they are same. And the figure displays a discrete Markov chain. However, if we increase the time steps, it will close to the continuous model. So when the time step becomes infinity, the DDPM is equivalent to the score-based models, and the SDE can be used to solve this process. In real-world applications, the data distribution at the left is much more complex than what we demonstrate. The data distribution usually has much more details. In this example, the diffusion or the distribution at each time slice is just 1D, and the distribution will gradually change as time goes by. The distribution will gradually lose details in the forward direction from the left to the right, and finally becomes a Gaussian distribution. In the reverse direction, the distribution will gradually show details and finally approximate the data distribution. So we can see this figure. So this shows a 2D diffusion process. At each time slice, it is a 2D distribution. And it changes the same way as the 1D example. Along the forward direction, the 2D distribution will gradually lose details and finally reach a 2D Gaussian distribution. If we move in the reverse direction, more details will appear and finally reach the data distribution. The data distribution will be arbitrarily complex depending on the data set. So real-world applications are high-dimensional. Here we show an example of diffusion model for the MNIST dataset. The resolution of the image is 28 by 28. This means the distribution at each time slice will have 784 dimensions. So in image applications, the joint distribution is high-dimensional and multimodal distribution. More specifically, the distribution dimension at each time slice equals the number of pixels of the image. We cannot show high-dimensional distribution, so we're just using 1D dimension for demonstration. Diffusion process is a process of adding noise to each data point. Denoising is a reverse process. It means moving towards the high density of the distribution. Here, we call the high density distribution MODA. It is a name for high density distribution in literature. Here, we show a distribution with 3 modas. The denoising process will move the data to one of them. So the figure shows the process of sampling. It starts from a point sampled from rightmost Gaussian distribution. And the data distribution or the data seeks the moda of distribution at each time slice along the reverse process. And finally, it reaches the moda of one moda of the data distribution at the left. We can see that the sampling process of diffusing model is a process of seeking modas of distribution along the denoising process. So under the sampling equals denoising equals seeking modas of distribution, and then equals move along the direction of gradient. So here we show an example of sampling process of continuous score-based model. The sampling process is similar to the discrete DDPM. The sampling process first sample from a Gaussian distribution on the right, and each sample moves along the high density areas of the joint distribution. And finally, it reaches the modas of data distribution at the left. The samples in the moda will have high quality because they share a similarity with many images in the dataset. The whole process is like balls moving along the valley of the landscape of joint distribution from the right to the left. The valley represent a high density part of the distribution. We just see how to sample randomly. As illustrated in the figure, the samples can be located in one of the three models of the distribution randomly. If we want to sample from the spatial part of the distribution, for example, the model cycled in the figure, how can we achieve this goal? And this is called the conditional sampling problem. The easiest method of conditional sampling is to train an extra model for predicting the gradient of the classifier, which is shown in the green formula in the figure. Then add the score to the original distribution, multiplying by a classifier scale W, which is colored by the red. This is called a classifier guidance. We can be used to balance the model coverage and sample fidelity. In other words, we can turn in the W to control how strongly we want to sample from the spatial classes. If W is 0, we just sample randomly. If W is small, the influence of the gradient of classifier is small, so it will generate variety of samples related to the class, but in relatively low sample qualities. When W is large, sample quality increase, but the generated sample are less diverse. In extreme, when the W is very, very large, the added distribution will be narrow and strong. This can lead to the model to sample only a single point from the distribution. It's just a single, always sampled for same images in this example. So the figure shows the sample from the method using classifier guidance. The class label is related to a type of dog labeled koji. It is clear that the classifier scale W has a great impact on the sampling quality and the sampling divergence. As we just discussed, in the left figure, the classifier W is equal to 1, and the sampling is diverse but does not produce convinced samples in the class. In the right figure, the classifier scale equals to 10. This method produces images have better quality and consistent with class labels. As we can see, the benefit of the classifier guidance is that this method provides classifier scale W to control the balance between the fidelity and diversity. Large W can generate samples with high fidelity. The shortage for this method is that it needs to train an extra model to estimate the gradient of the classifier. Thus, classifier-free guidance is proposed to overcome the shortage of the classifier guidance. The model can generate samples by just training a unified model and still have the ability to attain the trade-off between the sample quality and diversity, similar to that obtained using classifier guidance. This model jointly trained the unconditional and conditional model simply by random setting C to be unconditional classifier or setting C to the empty with some probabilities. Classifier-free diffusing guidance drastically improve the sample produced by conditional diffuse models at almost no cost. It is simple to implement and extremely effective. For extension, the classifier can be viewed as a constraint. Different constraints can lead to different applications. The diffusing model provides sample diversity, and the constraints provide sample fidelity. When the constraints are about to classify, as we just discussed, the model can be used to generate class conditional sample. The application also include imputation, carousalization, generating videos, and text-to-image applications such as Imagen and DALI, and lots of other applications. So let's check some two real applications in MR imaging. Let me introduce an application about case-based guidance. The case-based guidance is used to reconstruct MR images from undersampled case-based measurement. In this application, the undersampled case-based measurement provides the constraints. guiding the sample process towards the samples that are consistent with the subsample measurement, while provide proper detailed sample from diffusion models. So with no constraints, the trained diffusion model can synthesize high quality samples randomly, as illustrated in the left of the figure. Let's first check the formula. The undersampled measurement is written as a Y, and the signal X represents the MR imaging. Is measured partially by the Y with some noise. This formula shows the constraint between the X and Y. The figure below illustrates the sampling process as under the measurement of Y. In bluish box, these are constraints. The Y is perturbated to the latent Y hat T to apply constraint for each latent variable hat or X hat T. This figure illustrates the constraint applied to the latent variable. The sampling process at each step need to be consistent with the noisy version of the measurement Y hat. So the proximal gradient method can be used in case-based guidance, and the algorithms contains 2 steps as illustrated in the figure. The first step is to move along the gradient, and which corresponds to the sampling unconditionally in the diffusion models. The second step is to map the point sampled in the first step to the hyperplane imposed by the constraints, and continues this step until the sampling process ends. The final result will be consistent with the case-based measurement, while remain clean with the help of the diffusion model. In practice, we loop once per sample step. This is the result of case-based guidance. We use an 8 times acceleration mask to simulate the subsampled case-based signal. We compare with zero filling and compressing sensing techniques. The result shows that our proposed method achieves the superior performance on zero filling and compressed sensing. Here, I will introduce another application reconstruction of 3D MR images from diffusion model trained on 2D images. The name method applying 2D diffusion method is slice by slice along the one axis of the combine them. First, we sample the images slice by slice, and we combine them as a 3D images. And this leads to a significant artifact because the slices do not contact with each other. You can see that these artifacts clearly in the first columns of the figure. So how to solve the artifacts? The solution is to use a total variance penalty to force the slice to be consistent. The algorithm is similar to the case-based guidance. Besides the case-based constraint, we need to add another TV, this is total variance constraint in the projection, which restrict which need to enable slice to be consistent with each others. And we need to use ADMM algorithm to optimize these 2 constraints separately. The results are shown in the second columns of the figure, and the results are pretty good. So I will conclude this presentation using the 2 points. First one is diffusion model provides us the ability to wander around the landscape of the data distribution. And the condition and restriction applies in the diffusion model to the real jobs. So thank you. You have some questions.
Thank you very much for that. That's great.
All right. Any questions for Wei? I mean, mainly, there's some in the chat, I think, but I think this is really great because we've had a few talks today and we've gotten 3 different types of insights. I really like the way we had a data distribution vision of how things transform in diffusion models, which is really good. So we've seen a lot of different views. Is there any?
This is a typo. Yeah.
Oh yeah, it's probably a typo. That's right. It's fidelity.
Yeah,
Yep.
that's all right. Once a typo appeared several times, I started wondering if it was a new word. So
And thank you.
that's all right. Just on your last section where you're doing the I suppose inter-slice variations, I suppose the thing that arises in my mind is your risk of having a grid biased solution. So your answer is very much constrained by the looking at it in individual slices rather than thinking the whole problem in 3D. I have done some work on that before, trying to produce non-grid biased solutions. But any time you sort of do it slice by slice, you've got that risk of getting a staircase type result rather than a continuous result. Anyway, that's all right. Could take that offline perhaps.
Yep. Yeah, no, yeah, there's lots of issues when trying to deal with slice by slice. I guess you could use there's a huge number of different constraints you can try to keep things consistent. That's one way that they've done it there in that publication. I don't think it's published yet. It's still a preprint, right?
I published this one, not the last one.
Yeah, that one's your work, right? Yeah, that one looks really convincing. Well done on that one. Any other questions? Comment.
3D MRI paper and the archive paper. Can you go to the next slide? I didn't read the paper, but it seems like that's a compromise of applying 2D diffusion to 3D MRI dataset because we can't really do 3D at the moment because the dimension will be too high, like millions of pixels, and then diffusion memory just can't handle it. So they make this compromise that they still train on 2D diffusion, but somehow they manage to reconstruct 3D just incorporating some consistency along the slice dimension. But I think that's an open question that in MRI, we have a lot of real 3D problems that cannot be easily decomposed into 2D problems. But it seems like the diffusion models nowadays cannot handle these high dimension data sets. So I think that's a question that we can solve.
I think the principle of working in a semantic space, a perceptual space, rather than working in image space is interesting, which might apply to your problem. So it's quite likely that by sticking to image space, you're making the problem much harder than if you somehow manage to get that into a semantic space. So it's something to consider. So a lot of these problems are solved by working in semantic spaces.
By semantic, you probably mean latent space?
Yeah, a perceptual latent space that represents MRI images. If that could be, if you've got enough images and so on, you should be able to produce a space using a UNet type thing, and then do your solve your diffusion problem in that space, which is exactly what they did with stable diffusion, and that makes things much faster. So that they're doing it for 2D images. I see no reason why it doesn't extend to 3D.
Yeah. Brian, what about Fourier space? Is Fourier space useful?
Oh, it's very useful, but it's an old idea, isn't it? 60s, and we use that extensively, like in JPEG imagery and so on. You use a discrete cosine transform and so on, which is another example of being able to do things in a much smaller space. For image compression, but you can also do analysis in that at frequency space. But what I'm saying is, with these trained UNets, you can come to other spaces that are possibly much better than traditional downsampling spaces and Fourier spaces. It frees you up, and certainly everyone's focused on using traditional Cartesian grids, and my view is that basically if we go to a neural space, it's much more compact and it contains the information we want. We don't care about the images, we care about the information in the images. And if you preserve the information, you can go back to a high-res image. And so, you know, this could be a much more modern approach for these problems in MRI analysis.
Yep. Cool. There's some interesting thoughts there. I think we're pretty much over time at this point, so I will call it to a close. I just wanted to thank all of the speakers. Thank you so much for coming over and giving a talk. It's a lot of time out of your schedule. But thank you, Brian. Thanks to you and Christina and Wei and Hong Fu for sharing your ideas with us. So this session has been recorded, so I'll put the link up. We do have another session. What time is it now? So at 1 o'clock, we have a meet an AI expert. So I'll be around in the same room and things. I'll fire up the Zoom as well. So if you have questions or want to have some further discussions, also a Q&A on diffusion models and other things, you're welcome to drop by. And I'll see you then. So thank you very much.
I'd just like to make a comment. I did know you were catch up for lunch, but I've got some things to do and I'm working from home.
No worries.
I'd like to comment that I think this format is especially useful. I think the worst thing about this format is it's done once a year. And I'm not saying summer of AI, but you know, we should just talk a little bit offline about how we can sort of keep this momentum going throughout the year rather than, you know, I mean, this is a fast moving area. And I'd like to see, I suppose, there are a lot of seminar series in the school, but I've found that, like, when I was looking at these 3 or 4 years ago, hardly anybody was doing imaging. They were all doing, you know, database stuff and so on. And having seminars organized by a research group when there's no AI research group, to me seems a bad thing, because you know, you don't want to, if you go to a seminar series, you want to be in a situation where you find something interesting every week, not once every 5 weeks.
Yes.
Anyway, so let's talk about that offline. But I think we've got enough people in the school with similar interests in this area to do something far more effective in terms of research communications.
Yes, absolutely. And especially now we've actually got AI interns running throughout the year rather than just summer as well. So maybe, you know, we could line up with that schedule as well and do these similar things throughout the year.
Yeah, I think, you know, there's a space for like a 1 hour seminar. That's good, and you can fit that in. But there's also space for something more like this, even if it's just done on Zoom, a little bit more extended, or you know, looking at a particular, like a theme set of talks. We get 2 or 3 speakers speaking on the same topic and looking at it from different points of view. Anyway, let's discuss that offline. But you know, anything that sort of gets this area stronger in the schools is worth pursuing.
Excellent. Thanks for those comments, Brian. Let's go offline and have a chat about that. Yep. Thank you, everyone. We'll see you at 1 o'clock if you're around for that. But otherwise, for AI interns specifically, we have a hacky hour thing. So if you're having issues with your models or other things that you're trying to do, 3 p.m. It'll be on Zoom, but you will also have access to the computer lab, 78336. And I'll put some more information on Slack about that. But if you do need some computers with GPUs, it's down there, and there'll be an expert on hand to sort of help you debug or fix things that you might be encountering. All right. Thank you, everyone. And we'll catch you next week or later today. Thanks. Thank you.
Everyone, thank you.
Oh, no worries. Do you want?
I have meetings in the afternoon, so I cannot attend afternoon sessions.
That's okay. Thank you so much.
Yeah, that was great.
I was going to take you to lunch or something.
Yeah, I wish I could. I agree with Brian that we should do a seminar series on AI imaging. It seems that all these AI are data science, right? It's always data science. Yeah, very few talks there are